Hey everyone, and welcome to another lecture in Earth Science. Today we'll be covering Chapter 10, which covers glaciers, deserts, and wind. So glaciers are interesting because they kind of encompass two of the dynamic Earth spheres. The hydrological cycle, because they're made of water. So they grow through precipitation in cold areas, high mountain areas, and that precipitation comes from evaporation from the oceans, which is carried through clouds, and so that's all part of the hydrological cycle of our Earth. But glaciers are also part of the rock cycle, and the reason is because glaciers are heavy, slow-moving masses of ice that, under the influence of gravity and the landscape that they happen to be in, they'll grind their way through the exposed rock on the Earth's surface, and that grinding causes a lot of different types of rock falls, and they scour the valleys and they pick up and create a lot of sediment. So essentially they're converting a lot of rock into sediment, and that sediment can then be carried by meltwater, by wind, further downhill into depositional areas like the ocean or a lake. And then that becomes part of the rock cycle, because ultimately then you create sedimentary rocks, and this process could repeat itself. But let's get down to the definition of a glacier. Is a thick mass of ice that forms over land from the compaction of snow, right? So precipitation falls in these high mountain areas or areas of very close to the poles, and the weight of the snow just continually compacting layer after layer will cause the snowflakes and the water to recrystallize into a new form and become ice. Okay. And glaciers themselves, they leave behind a lot of geologic evidence, or they carve the landscape in very obvious ways, and we can use that as evidence to understand, one, what the climate was like in Earth's past, and two, how far did these glaciers expand in certain areas, how far did they retreat, just things like that. There's two types of glaciers. There are valley or alpine glaciers, and these originate in high latitude or high elevation mountainous areas. So they fill up the kind of valleys in between the mountains, and they're essentially like slow-moving rivers of ice, heavy ice, kind of carving their way through this rugged terrain. And you can see clearly that this ice, it's hard to tell scale here, but just imagine like this is the size of a very large river, so to speak. Okay, and these are just a lot of, on the surface, a lot of crevasses or cracked ice, and then below the surface it's more plastic flowing ice, but it's still a solid. And all of this moves very slowly, but it moves and kind of moves toward low-lying areas. So those are valley or alpine glaciers. There can be like a number of different valley or alpine glaciers kind of coming away from a mountain, or they converge on one another, but they're strictly kind of confined to those mountainous areas. The next type of glacier are ice sheets, and ice sheets are different because they are absolutely massive. They're also referred to as continental glaciers because this ice covers entire continents. I don't know if you're aware, but Antarctica in the southern pole is a continent. It's huge. I'm sure you're aware it's a continent, but I don't think you might know how big it is. It's 1.4 times the size of the United States, and it's covered in ice. in this massive ice sheet, and essentially the ice covers the entire landscape, and the only things that are visible are high mountainous areas that kind of peek through the actual ice sheet, which is incredible. So just Antarctica itself is bigger than the United States, and it's covered in ice. By the way, that ice on average is 2 kilometers thick. So imagine coast to coast, from East Coast United States to the West Coast, just covered in ice, and on average 2 kilometers thick. Okay, so that's a lot of water, that's a lot of ice. It's really cold in Antarctica. Some of the bases on the continental margins have an average summer temperature of 0 degrees Celsius, so that's 32 degrees Fahrenheit. So the average summer temperature is freezing. We also have ice sheets in Greenland. All right, Greenland is the one place where there are continental glaciers or ice sheets in the northern hemisphere. In Antarctica, that's the southern hemisphere. That's an absolute massive place. Okay, it kind of, you kind of forget about it, because when you look at a flat two-dimensional map, it's just on the bottom, and you're just like, oh, whatever. It looks like it's split up everywhere, but it's a massive continent. And then about 18,000 years ago was our last glacial maximum. Okay, our climate was vastly different 18,000 years ago. We had huge continental glaciers on North America during this time. And so a lot of these ice sheets and continental glaciers expanded to other continents when Earth was much cooler than it is today. Now in the northern hemisphere, there's a lot of sea ice. There's also sea ice in the southern hemisphere, but because Antarctica is kind of like sitting right at the South Pole, there's land sitting underneath that ice. And in the North Pole, if you go to the geographic North Pole, there's no land there, so there's sea ice that forms, and that's essentially just a cap of ice that sits on top of the ocean. It can be anywhere, if it's just forming, a couple centimeters thick to a few meters thick. Okay, and then that kind of expands and contracts with the seasons, going through winter and summer. And they also create ice shelves into the ocean, and that's when you have ice sheets that kind of empty out or just sit on top of, they kind of go past the continental margin and then sit on top of the water. That's very prevalent in Antarctica. Now there are other types of glaciers. There are ice caps. These are kind of, I guess, smaller areas, smaller scale in comparison to ice sheets. We can find those in like Norway or Iceland. There are areas where ice kind of completely covers the landscape, and a lot of times those can feed the other Alpine glaciers, or what we refer to as Piedmont glaciers. Piedmont glaciers are just glaciers that empty out into flat-lying land areas, and then the glacier itself kind of expands into a fan-type shape. Okay, so here's an image showing you the major ice sheets that we have in the North Pole. Here's Greenland. Okay, that ice sheet, I think, it's approximately, well, the Antarctic ice sheet is around 14 million square kilometers. So that's really big. So that's here. This is Antarctica. Again, larger than the United States in terms of land area. Okay, right at the southern pole. Here's an ice shelf, the Ross ice shelf. So that's sitting over water. But the motion of the ice is very complex. You have to kind of find out where the ridges are of the land, but it's difficult to do that because it's covered by ice. But you can use like modern instrumentation, radar altimeters, to figure out the land surface beneath the ice. In some areas in Antarctica, the ice is as thick as 4 kilometers, which is impressive. But in Greenland, it's a little smaller. It's only 1.7 million square kilometers. But it covers about 80% of the island. All right. So those are your ice sheets. Okay, so how in the world do glaciers move? They move really slowly. If you've ever been to one, or you can just YouTube Calving Glacier, They can move on to low-lying land areas, or they can kind of empty out into the ocean, into a bay. But you can see the front of a glacier. That's kind of like where the glacier ends, or its terminus. That's where you can see the fastest movement, because and it's more dramatic too, because large pieces of ice are just going to either just break off and fall into the ocean. But what that is fracturing. Okay, so the upper 50 meters of a glacier. Okay, so if we have say we have a glacier, I don't know, this kind of looks like a glacier, let's say. It's moving in this direction. Okay, block glacier. The upper 50 meters behaves brittly, meaning that like the ice will fracture, and that creates really large gashes on the surface of the ice. Okay, we call those crevasses, and the crevasses can be as deep as 50 meters. Right, so let's just say this is 50 meters. All right, so that's why it's kind of dangerous to kind of walk on top of a glacier, because this area is unstable. It's very brittle. You could fall in to lower areas in this zone of fracture. Okay, and if it's like an Alpine, glacier, there'll be mountains around it. There are going to be rock falls, let's say, and then essentially a lot of sediment or large pieces of rock can fall on top of the glacier and then gets essentially piggybacked on a ride down towards a low-lying area. And essentially, so there's the below 50 meters, this area, this moves a little differently. Okay, the velocity is a little faster in the center of the glacier and slows down wherever it's contacting the ground because of friction. But we refer to this as plastic flow. So what happens is the weight of 50 meters of ice, above this area, will cause the water molecules to kind of squeeze together in their solid structure, and then allows for it to move in kind of layers. So it kind of shears along these layers in the crystal structure. So the movement resembles plastic flow. Okay, and then on the ground, on the floor of the valley, where this ice kind of just scours the floor. It moves because there's a little bit of meltwater that forms, and then there's slippage. Okay, so that's essentially how a glacier moves. All right, here's an example of a crevasse, and an extreme earth scientist, exploring the upper levels of a glacier. So what's really important to glaciers themselves and how they move is understanding the glacial budget. And a budget essentially is how much snow the glacier is taking in versus how much ice it's losing at its terminus, or the glacial front. Okay, so the zone of accumulation is the area where the glacier forms. So those are typically higher up into the mountains. They a lot of times begin at these features called cirques. And so if there's precipitation there, snow accumulates there, and that would be the zone of accumulation. The zone of wastage is just the end of the glacier, and that's where you have loss of glacial ice because of calving or just melting, and then they become little meltwater becomes little braided streams and stuff like that. So if you have more accumulation, right, more snow accumulating at the higher elevation areas versus material that's being wasted, that means the glacier's front is going to advance, right? And that typically means cooler overall weather on Earth. So if you have more accumulation, the glacial front advances. However, if there's more wastage and less accumulation, so there's more wasting rather than accumulating, then the glacial front is going to retreat, and so it's going to move further back up into the mountains. And when those two things are balanced, then that means that the glacier will advance in the winter and retreat in the summer, but every year it'll advance and retreat to the same areas they were before. That's when the glacier is kind of in balance in terms of accumulation and wasting. Okay, so here we go. There we have a picture of a glacier. I should have just said that here. Okay, so here's the snow line, the zone of accumulation. So here it snows and it adds material to the glacier. At the end, you can see here, this one's just ending on land. So a lot of it just melts away into these streams. And you can see the cracks here. This is the zone of wastage, right? So if there's more wasting than accumulating, this glacial front will move in this direction, okay? However, if there's more accumulation, then the glacier will expand, cooler temperatures, and kind of have its front over here, okay? So down here you would see the slippage and the plastic flow, and then the upper 50 meters is just piggybacked on top of everything else kind of moving downwards, okay? I also want you to notice, do you see this brown stuff here? This is a lot of sediment that's being essentially bulldozed down the mountain towards low-lying areas. Think about that. Like think of a bulldozer kind of with its blade down, and it's just pushing sediment forward. And then the glacier essentially does the same thing. It just pushes all this sediment forward, and it advances as far as it possibly can during the winter time, and then it recedes during summer. And then as winter comes again, it does the same thing and bulldozes and pushes more sediment to the area that it was once there before. So huge piles of sediment can be left behind from glaciers. Okay. Unfortunately, with our warming climate, glaciers are unbalanced and they are actually retreating. So here's some time-lapse photography of a glacier in 1935. This was on the southwest coast of Greenland, and in 1935, this is where the glacier front was. Okay, and then in 2013, from a similar vantage point, it's all begun. This is now just meltwater, and this is those kind of lakes, which is sad. There's some other alarming statistics. About 150 years ago, at Montana's Glacier National Park, so that's in the United States, our Glacier National Park, 150 years ago, there were 147 glaciers. Now, today, only 37 remain. So a lot of glaciers have been disappearing because they're unbalanced, and that's due to the warming atmosphere and CO2 emissions. They're probably going to have to rename Glacier National Park. It's just going to be Glacierless National Park. I don't know. But if this trend continues, right? Okay, so going back to glaciers being like bulldozers, they help erode the surrounding bedrock. They do a really good job of this. And they do this by plucking. That's the actual term. See, what happens is, say you have a little bit of meltwater, right? This is a very cold region where there are glaciers. So meltwater infiltrates the kind of like the cracks and joints of rocks, and that water can freeze. And when it freezes, as you know, ice expands. And so when it expands, it forces larger cracks into the rock. And then it essentially can pluck these rocks straight from the bedrock, and then that rock can be carried either within the glacial ice, or sometimes if there's a landfall, a lot of rocks can fall on top of a glacier and then be piggybacked for a ride as it goes down to lower lying areas. So plucking occurs as it kind of picks up rock. Now glaciers also, not only do they just essentially break rock and take it for a ride, but they also polish and abrade the rock as they pass through it. Remember, like water's heavy. Fill up a Home Depot bucket filled with water and lift it up with one arm. Water can get pretty heavy. Now imagine, hundreds of meters of ice, solid ice, kind of slowly, centimeters per day, moving downhill, slowly grinding anything that's beneath it. Well, that's what happens. So glaciers will actually polish the surface of rocks, and this is evident in any place that has had glaciers in the past or today. You can see the evidence of glacial abrasion on the rocks. And it pulverizes the rock too into really small kind of powdery material. We call this rock flour. And what that does is that makes these glacial lakes this kind of really light green hue, which is really beautiful. And that's why it has that light green hue, because of all this pulverized rock flour. In addition to that, sometimes like small pieces of sediment can be just inside the glacial ice, right? And that sediment will essentially grind against the bedrock and leave behind kind of grooves, and we call those striations. All right, I think I have pictures. There we go. So here you can see the striations as a glacier moved in this direction over this bedrock. And so a lot of glacial scientists or earth scientists will study these striations and determine the direction of glacial movement in the past, right? One place to look at, especially polished granite, would be Yosemite National Park. Look at this rock right here. It's almost perfectly polished. It's like as if you grabbed sandpaper and just, sanded down the rocks, okay? And you can see clearly that glacier had some sediment within the glacial ice, leaving these huge scratch marks, right? And so in places like Yosemite National Park, right now in those valleys, there aren't glaciers in the low-lying valleys, but clearly in those low-lying areas, the granite there is very polished, and they show evidence that glaciers once kind of moved through the valleys in that national park. So this glacial erosion causes or creates really nice landforms. Okay, there are a bunch of different terms. The next image, I'll be able to show you all of them, but there are glacial troughs, hanging valleys, cirques, aretes, horns, and fjords. Okay, so in a typical landscape where you have running water just kind of carving its way, creating V-shaped valleys, okay, this is what you would have. But let's say the climate changes and you start having glacial formation. All right, what you'll have, see, these are V-shaped valleys. When glaciers kind of make their way through the landscape, they'll essentially erode out the entire valley and create it like as if it was U-shaped. You see that? Okay, you see these U-shaped valleys. I'll show you a picture where it's pretty obvious, but that's how you know when you see a landscape that has U-shaped valleys, you could tell, ah, man, there used to be glaciers that once moved through this entire area. So here's the main glacier moving downwards. Okay. Now here is a mountainous landscape. Okay, cirques are these areas a lot of times where a lot of it's where the zone of accumulation is, and this is where kind of glaciers begin. Okay, and there are kind of circular features closer to the higher areas, the higher mountainous areas. And when you have two glaciers kind of parallel to one another like this, they're going to erode out the rock that's next to them and create this very high and thin ridge, and we call those aretes right here. So you can see that these are really, I guess, skinny ridges in between a couple of U-shaped valleys here, and they're created because of two kind of running glaciers parallel to one another. And what you ought to also notice too is that the main glacier erodes deeper than these kind of smaller, like feeder glaciers. Okay, and so what that leads to is that these U-shaped valleys are like elevated or perched above the main glacial trough. So we call this a glacial trough. And so what that leads to is a hanging valley, which you'll have a very beautiful waterfall that will form. And you can see that in Yosemite National Park. This is, I think this is Bridal's Veil waterfall there. And essentially here, there was a glacier up here that has since melted away. There was the main glacier was down here, and now there's a huge height difference between the two valleys, which creates a spectacular waterfall. And then here's another cirque, right, at the beginning of another glacier. And then if you have a number of cirques kind of forming and emptying out into like different directions, what that eventually creates or can create is what we call a horn. And a horn is like what's pictured here is Matterhorn in Switzerland. But here you have glaciers kind of eroding each side, different sides of this, leaving behind kind of almost a pyramid-shaped rock feature. And it happens over time because these cirques will expand and get larger and larger, and then they kind of coalesce into one another. And as they do that, then they leave behind the kind of pyramid-like horn structure. Okay, so if you ever go to places like Norway, Switzerland, it's the Sierra Nevadas, places where they, Alaska, you'll find landscapes with these features. Okay. A lot of sediment is created by this process. Okay. Glacial drift is any sediment that is of glacial origin. And so what that essentially means is just it's material that's moved by the glacier, or the sediment that's created by the glacier. And then in the summer, as the kind of glacier recedes and melts away, a lot of that sediment is deposited out of that melting glacial ice. And so it includes sediment of all sizes. It includes pulverized rock flour, so clay size or sand size material, all the way up to giant boulders that were just piggybacking on top of the glacier. So geologists refer to this material as till. Okay, till is stuff that's or sediment that's deposited directly by ice. And then drift itself is the sediment deposited by the subsequent meltwater. So the ice pushes a lot of sediment down. As it melts away, then the water itself can push that sediment further along its journey. And so when you look at glacial till, here's an example of one, you'll notice it's a lot of material with varying sizes. So a lot of fine material and a lot of boulders and cobbles and sand and all types of materials, just a mix of unsorted different sediments. And another telltale sign that this is related to glaciers is that a lot of till will show evidence of scratching, right? So maybe it was stuck in glacial ice and then it just was like scouring the bedrock as it kept moving downhill. So as a result of all this sediment, the glaciers themselves leave behind these deposits, and year after year, if you have a balanced glacier, it's just going to continue to deliver more and more sediment from the mountainous regions down to the low-lying valleys. And so these depositional features arise from this. One are moraines. Okay, these are layers or ridges of that till material, sediment of a lot of different sizes. Remember, those glaciers are like bulldozers. They just push all this material down to the furthest they can go during winter, melts away during summer. Next winter, boom, it does it again and brings more sediment to its end. And those are moraines. Okay, those are huge ridges of till. Like you can, some of them can be, like 40 feet off the ground. It's like a little ridge that you have to climb and then get down. That's just material left by a glacier. And there's different types of moraines. There's lateral, medial, and ground moraines. Let's show you some pictures. Well, this actually, these are end moraines in the Great Lakes region. Okay, and so these are areas that have been mapped showing the extent of past glaciations on the American continent. So today, obviously, in Minnesota and Michigan and places like Illinois or Ohio, Indiana, there are no glaciers there today, right? But we today see the evidence or the moraines or the huge piles of sediment that were left behind from recent glacial advance. So during much colder times in Earth's history, like 18,000 years ago, and many times prior to that, this part of the United States was covered by glacial ice. As far down as over here. This is the extent, the coldest extent or evidence of glacial tills and moraines down in this area. So imagine this entire area being covered by thick ice, right? Hundreds of meters thick. That means the areas just south of here must have been a lot colder. during those times. Okay, so there are other depositional features left by glaciers. There are outwash plains and valley trains. I'll show you pictures: kettles, drumlins, eskers, and kames. Okay, here's the all-encompassing picture. So here's a retreating glacier. Okay, this is what I'm talking about, the end moraines that form. Okay, and so this is the glacial till that's left behind. So they end up kind of being like ridges that form, and in between those ridges you can have low-lying areas that fill up with water. We call them kettle lakes. A lot of times perhaps the glacier plucked out a lot of material here, creating this low-lying area, and so that's what a kettle lake is. The rivers that meltwater kind of move through, remember they're moving through a lot of unconsolidated sediment that was deposited here by the very thick glacier, and so they become braided rivers. And so you can see that these rivers have a lot of, they're sinuous and have a lot of breaking streams, braided streams through all the banks of sediment. Some terrain over here, we call this a drumlin field, and this is an individual drumlin. Those are parallel hills made of till. Okay, drumlins are kind of streamlined and asymmetrical hills, and they're mostly just composed of a glacial till material. They can be anywhere between 15 to 60 meters in height, and their average length is about half a kilometer, or half a mile, excuse me. Okay, and so the steep side of the hill faces the direction from which the ice advanced. So that would be, this is the steep side of the drumlin. So that indicates that the glacier moved in this direction. So you can take a look at the landscape and interpret the landscape and figure out the direction of the moving glacier. And eskers are just kind of sinuous piles of sand and gravel that form from meltwater in a river, kind of moving material back and forth. Same thing with kames. They're kind of just pock-marked hills of till material kind of depositing from the glacier. All right, so those are the typical landforms. So you'll see this in western New York, a lot of drumlins, the Finger Lakes, for example. Here's an esker that you can see here. So when we have ice ages or times when Earth is much colder than normal, that has huge effects on obviously the Earth's climate, but the migration of animals to newer areas. Like if you have during summer times, organisms can migrate towards areas that were once covered by glaciers, and then when the glacier comes back, they have to move back south. But if we have if these change in the climate and it starts getting warmer, these glaciers start to recede, then animals can migrate and start exploring areas they couldn't have before. And vice versa, if you had a cooling Earth and the glaciers all of a sudden started to encroach on areas where they weren't there before, organisms are forced to migrate further south, okay, or away from those glaciers. So these kind of disrupt the ecological areas where that encompass plants and animals, and so that can happen as a result of onset of ice ages or going into an interglacial period. Another thing is when you have glaciers kind of disappear, they're really heavy and they depress the land. And so what happens is the land holding that glacier will sink as a result of holding all that weight. And then when the glaciers are gone, all that weight's been removed, the ground actually, the ground actually rebounds and moves upward. So for example, in Norway, a place that was covered in glaciers during the last glacial maximum, 18,000 years ago, they're actually seeing sea level fall in a number of towns there, despite the fact that sea level is rising today because there's a lot more water going into the oceans because of warming climate and thermal expansion. Their crust in Norway is rebounding from the last glacial maximum. So their land is rising at a faster rate than sea level is rising. So for people who live there, it appears as if sea level is falling. Okay. Anyways, when we go through ice ages and interglacial periods, there are worldwide changes in sea level. Sea level can fluctuate up to 600 meters higher or 600 meters lower, depending on if it's colder, more water will be locked up on continents at lower sea level. If it's warmer, all that water that's on continents and glaciers goes back into the ocean. So that would make sea level rise. And just as an example, if all the if the ice sheet in Antarctica melted and kind of was added to the ocean, sea level would rise about 56 meters or 180 feet. And that, yeah, that would be disastrous for a place like Florida. Rivers will change direction. When you have like a lot of glaciers, they alter the landscape so they can change the kind of drainage patterns on land. Glaciers can also act as dams to create temporary lakes in certain regions, so then you actually get deposition there. But as those glaciers recede, you can have catastrophic events where water just comes rushing down and filling a low-lying area. And then you have the formation of really high-altitude lakes. We call those pluvial lakes. Okay, so here's an example of changing sea level. 18,000 years ago, our last glacial maximum, continental glaciers, there's evidence of them existing all the way down. Look, this is like through Ohio, this is through the Midwest, all the way in these areas. This was all thick ice, okay? As a result of that, sea level fell during that last glacial maximum. Or you can look at it one way. This is today, right? This is our current sea level, and over the past 6,000 years, we've had pretty stable sea level. But 18,000 years ago, sea level was about 330 feet lower than it is today, right? So from 18,000 years ago towards today, sea level has been rising and then hit this plateau, and it's been here for a while, okay, kind of constant. But during this time, sea level rose about 330 feet, okay, from 18,000 to about 6,000 years ago, all right? But during this time, 18,000 years ago, here's mean sea level, by the way, and this is thousands of years ago, just so you know. Our coastlines look different as a result of sea level falling. Look, Florida essentially doubled in size. Like if you were in Tampa, you'd be about 150 miles away from the coast. So Tampa, St. Petersburg, you'd be considered Central Florida. Suckers. Look, it expands all the Gulf Coast states. Mexico is larger. The Yucatan gets larger. The Gulf of Mexico is tiny. I mean, honestly, Florida almost becomes part of the islands here, Cuba and Bermuda. I'm sorry, Bahamas. Excuse me. Okay, so let's talk about ice ages. Ice ages began about 2 to 3 million years ago. There were ice ages before that. We have geologic evidence for that. But our current kind of interglacial glacial cycles have been kind of repeating themselves over the past 2 to 3 million years. We specifically, or geologists specifically, gave this division of time its own name. It's called the Pleistocene epoch. Okay, and ice has covered about 30% of Earth's land area, and it's twice as extensive in the northern hemisphere. And there are a number of factors for that. There's more land in the northern hemisphere. There's more land that's further or at higher latitudes than in the southern hemisphere. I mean, the exception's Antarctica, but you've got the entire Eurasian continent and North America, Canada, Greenland, all those places. So yeah, look, take a look at so these kind of lighter shaded areas were sea ice, and then all that sea ice connected with the continental glaciers in Canada, in Greenland, in the Alps, and in Russia. So excuse me. So you can see that the extent of the continental glaciers kind of moved into a lot of the Midwest, which is really incredible. Okay. So this is where all the ice was during our last kind of glacial maximum, or whenever we would go into these cooler phases or ice house phases. So what causes these ice ages? Okay, in order to explain them, you must have a hypothesis that can explain short climatic changes in our weather, as well as the continual cooling of Earth or warming of Earth, like whatever those reasons are. And so it has to be vigorously tested. So, you know, Earth scientists have been doing this for a while. They're trying to really pinpoint exactly what the causes are. And one of the potential causes, and actually has been the cause of, excuse me, ice ages in geologic past, like deep geologic past, is the location of continents or plate tectonics. Okay, if we had more continents just so happened to be near the poles, that would help induce more ice sheets forming, right? And if you have more ice sheets on continents, that would affect the albedo on Earth. Albedo is the percent reflectivity of solar radiation. So if you have more ice covering land, that's going to reflect more solar radiation back out into space, and that will cool down Earth, right? That can also alter ocean circulation as well. Okay, so if you have one great example of this is Antarctica wasn't kind of a continent on its own in the southern hemisphere, like by the southern pole forever. It used to be kind of connected to South America, and it used to be very north, like, or much further north. And a lot of the warm tropical waters would actually hit the coasts of Antarctica, and it wasn't frozen over as an ice sheet. But through geologic time, it was about 20 million years ago, Antarctica became isolated as it moved further southward, and then ocean circulation patterns changed, and it became isolated, and no more warm tropical water would make it south towards Antarctica. And it froze over, and now there's a huge ice sheet over that. And because of that, when that happened 20 million years ago, there was a major cool down in Earth's history as a result of that. Then, as we've talked about during the kind of formation of Pangaea, remember we talked about Alfred Wegener's evidence of glaciers on land in these various continents. So that was an ice age. That was the late Paleozoic ice age. And so this is the area that was the extent of continental glaciers during that time. Now the configuration of the continents were very different then. Okay, and so this is that, you've seen this. This is our kind of modern day, and then here's the leftover evidence of glacial landscapes as a result of that ice age during that time. But what scientists have really focused on and tested vigorously, and is kind of the best explanation on why we have this cyclical every almost about 100,000 years of glacial to interglacial period, is because of variations in Earth's orbit. These were calculated by a scientist named Milankovitch, and he proposed the Milankovitch hypothesis. And there are three ways in which our orbit varies. There's the shape of our orbit. That's referred to as the eccentricity. So the Earth will vary in terms of how circular our orbit is. Our orbit is elliptical, but over the course of 100,000 years, it kind of waxes and wanes, becomes more circular or more elliptical. Okay, the Earth's angle or our obliquity changes as well. That affects how much solar radiation we'd be receiving. And again, we have a wobble on a shorter time scale. We call that precession. Okay, and so changes in our climate over the past several 100,000 years have been very closely associated with these changes in our orbit. And so the reason why orbital variations kind of picked up steam in terms of correlating well with global changes in our climate, a couple of reasons. One, the plate tectonics, say for the last glacial maximum, which was 18,000 years ago, that's too short of a time scale for plate tectonics to be the reason for that climate change. So over the past, and even if you go in the order of millions of years, the continents move so slowly there must be another explanation for why we go through these glacial ice ages and interglacial periods. And orbital variations kind of have a more, I guess, respectable time scale that correlates well with the major changes we see in our climate from the rock record and from other records like ocean sediment record. And scientists have been able to correlate really well the ocean sediment record with changes in microorganisms due to changing climate, and it lines up really well with these orbital variations. So here's the example, or all of the examples. This is the shape of the orbit, so this is eccentricity. So when we have a more circular orbit, we have less varied seasons, so, or I guess seasons extremes aren't as crazy, like the difference between summers and winters, hot summers and hot winters, because if we have a more elliptical orbit, certain times, it's not the cause for the seasons, but it can make the seasons more dramatic, or colder winters or warmer summers if we have more elliptical orbits, okay, because that affects our distance towards the sun and how much solar radiation we receive, okay. And then in addition to that, this is the tilt. Right now we're about 23.5 degrees is our current tilt of our axis, and this varies between 24.5 degrees and then to 22.1 degrees. And so when we have a larger tilt, our poles will be also subjected to more, when you're tilted away from the sun, you receive much less solar radiation, so much colder winter. And then when you're tilted kind of on the other side of the Earth, tilted more towards the sun, then you receive more solar radiation. So that can alter our climates as well. And then finally, the precession is like a spinning top. Over time, our Earth wobbles just a little bit, and that can also affect our long-term climate. All right, so let's shift gears all of a sudden to deserts. Deserts occur anywhere where there's a water deficiency, where evaporation exceeds precipitation. Okay, typically warm areas. On Earth today, there's around 30% of the land surface are covered by these dry areas or deserts. Okay, the distribution of deserts and dry land on Earth is no accident. There's actually specific reasons for that. The first one is the air circulation. So at certain latitudes, specifically the Tropic of Cancer and Capricorn, there's a lot of descending air from the upper atmosphere, a very high pressure, low moisture, and that's what contributes to deserts in those regions. If you have a massive continental landmass, a lot of times the interiors don't receive a lot of precipitation because they're further away from the ocean, and the precipitation that arises from all the evaporation over the oceans and stuff like that. And then also deserts will form behind high mountain areas because they act as kind of like a barrier that wrings the moisture out of the atmosphere before that dry air then passes over these regions. So deserts are in areas for a reason. Another one could be also ocean currents. Put that in there. There are ocean currents that are derived or they originate from high latitude areas and then move towards lower latitude areas, and they bring a lot of cold water from the poles to certain sides of continents, and that cold water is often accompanied by colder air, drier air, and that also helps create desert-like environments. Okay, so there's two. Deserts are the most arid and dry areas. So again, by the tropics of Cancer and Capricorn is where we find a lot of deserts. Here in southern Africa, we have the Namib and Kalahari correspond to that descending dry air. The sandy deserts and deserts on the interior of Australia. So that's a double whammy. It's kind of the interior of a continent. And then also right at the Tropic of Capricorn, The Atacama Desert here is close to the Tropic of Capricorn, but also there's a lot of cold ocean currents that move northward here that attributes to that. Okay, the Sahara is, and the Arabian and the Indian deserts are all smack right on the tropics of Cancer, and that's where you have descending air that's very dry, as well as a lot of the deserts in Mexico and Southwest United States. Okay, and then here the deserts are associated with being in the deep interior of a continent. Then surrounding the desert environments, there are steppes. These are semi-arid environments that could become deserts, but again, these are very dry landscapes. Okay, the processes that work in really arid climates occur. These areas, because they're so dry, water isn't obviously as effective as in humid regions. However, in deserts, it still rains, and when it does rain, a lot of the material is unconsolidated. So water does a lot of work in deserts, moving sediment around, especially because there's not much vegetation in deserts. But another factor in deserts is because it's dry, you have wind is a big factor in terms of moving sediment in deserts. Okay, mechanical weathering still is in play. That you have unaltered rock and mineral fragments present and eroding and in deserts, and some chemical weathering does occur. And this is why you see a lot of times the rocks in desert regions have that kind of like rusty color. That's the oxidation from the ferromagnesian minerals that are in those rocks. And they form very thin clays and very little soil forms in these types of climates. So water does play a role. There are ephemeral streams meaning that they're dry most of the year and they only run when there's a specific rain event that occurs. Okay, so desert rainfall typically happens as heavy showers, and as a result of those heavy showers, that can cause a lot of flash flooding, and that can be kind of dangerous. There are areas, for example, if you go to Zion National Park, there's an area where you can walk along the Virgin River and walk through it essentially in these really steep slot canyons. And if there's a desert rain there, a lot of water can just essentially funnel into these low-lying areas, and the water level can rise like 18 feet in a matter of an hour or so. So that can be very dangerous. And that's because they have a very poor drainage. Okay, and most of the erosional work is done during these few times of rain by running water. Okay, so here's an example of an ephemeral stream. Here's the dry riverbed. If you ever go out hiking out west, you might kind of walk through these and be like, oh, whoa, what's going on here? And during those rarish rains, this whole area will flood, and you get that flash flood and flowing water. You can go on YouTube and just do desert flash flood, and it's actually quite soothing to listen to just water just kind of move through a desert area. Okay, so the Basin and Range province, which is an area out west, it's essentially the entire state of Nevada. This area of the western United States is consistent of uplifted crustal blocks as a result of tension. So the entire area there is getting spread or pulled apart. So it's a tectonic process where the crust is actually thinning, and then you have these faulted blocks that move downwards and become valleys, and then the other blocks are kind of pushed or kind of slide upwards, and those are the uplifted kind of ranges. And so in the Basin and Range province, you'll run into like a valley range, or basin range, and they're all kind of almost all closely north-south oriented ranges and valleys. And there's no, when it rains there's no drainage that goes like out to an ocean. A lot of this water just kind of drains right into those low-lying valleys. And so they create these temporary lakes. They call them playas. And these lakes because it's so dry and hot there, they eventually evaporate away, and then they leave behind kind of like these salt pans, which are pretty crazy. And it's just left behind material that was in the water, and it recrystallizes into an evaporite, which is pretty cool. And then at the edges of the mountain fronts, you'll find alluvial fans and bajadas. These are just features of sediment being deposited by this temporary rush of water. Okay. So eventually, the kind of landscape evolution are these mountains will be eventually reduced to kind of knobs, and these are specific terms, inselbergs, and they project above the valley floors where there's a lot of sediment filling in. So here's the Basin and Range province, like I said, entire state of Nevada right here, and it goes into Mexico. We don't include it, but this whole area is being spread apart, and the crust is actually thinning. So what happens is you get these downdropped valleys, okay, and then here are the ranges that are eroding away. All that sediment fills in. These are the alluvial fans and bajadas, okay, and then all this water fills up these temporary lakes called playa lakes, but they evaporate away and leave behind a lot of salt and evaporite material. It's usually typically kind of white, and then but over time these ridges will weather away, and all that sediment will fill into these low-lying areas, and this is a late-stage evolution of an area like the Basin and Range province, which is a desert region. Okay, and then there's wind erosion. Wind does a lot of work as well, but it's kind of a fraction of what water does. But when there's high winds, it can pick up sand to clay to silt-sized material up in its kind of updrafts and stuff like that. We call this deflation. Okay, that's the lifting of loose material, typically very light material, small sediment that gets lifted out. These produce blowouts, which are areas that have just, I'll show you a picture, just blows out all the material. And then in deserts, what you'll see is the deposition of a lot of this loose material called desert pavement. Okay, let's see if we got a picture here. Well, here's just an example of wind's suspended load. The suspended load means stuff that's up in the air. Okay, the Saharan dust plumes can come off the Sahara. This is going into the Red Sea. Here's the Saudi Arabian Peninsula. So this dust plume is affecting the people here locally, but Saharan dust can be lifted over the Atlantic and deposit in the Caribbean, even in Florida, and it can cause like the sunsets to be kind of reddish as a result of these fine particles being picked up into the upper atmosphere. All right, so and then this is the desert pavement. This is how it forms. There's two kind of competing theories. One is deflation and wind remove all the small particles, only leaving behind the large particles that it can't carry up into the that can't be lifted up because they're too heavy by the wind, and so eventually you get left behind with just a lot of loose gravel and cobbles, or over time this wind-borne material, fine stuff, gets deposited on these weathered pebbles and bedrock, and then through those rains gets forced underneath them. So those are the kind of two competing theories on how desert pavement forms. But if you've ever been to a desert, you'll notice that a lot of times in really remote areas, they don't pave roads. There's no need for it because you can just drive on this very flat desert pavement. There are other deposits, or deposits that are created by moving wind, are called loess deposits. This is wind-blown silt, and these can deposit over really large areas. The sources of this wind-borne material typically comes from deserts, also from areas that may have had glacial stratified drift. So this would be very light material being pushed around by meltwater. That can be lifted up by prevailing winds or strong winds and then carried and deposited in a different area. And some of these wind deposits will create sand dunes. Okay, sand dunes are just mounds and ridges of sand that form as a result of wind pushing sand back and forth throughout a really dry region. Okay, the slip face of a sand dune. That's the leeward slope of the sand dune. And then there's another feature of sand dunes called crossbeds, and this is where sloping layers of sand kind of overlap and cover other layers of sand. Let's see if I got a picture. Yeah, okay. So here's the idea with sand dunes. Here's the kind of gentle slope of the sand dune, and then there's a steeper slope down here. And then so these would be the sand dunes forming as a result of prevailing winds kind of continually pushing in this direction. So here's the slip face. This is the kind of steeper edge of it. Okay, and so what happens is sometimes the prevailing wind can change, and then let's say the wind starts blowing in this direction. So now it starts changing the sand topography, so to speak. Okay, and then now the slip faces are on the other side, and what this does is creates what we call a cross-bedded feature. And this sediment, if it ends up becoming a sedimentary rock, can be shown in sandstone. This is at Zion National Park. The Navajo sandstone, which is an extensive exposed unit there, shows cross-bedding. And what that helps tell us is that during the Jurassic, when the Navajo sandstone was being deposited, that was in that part of Utah, we had shifting sand dunes like you would see in the Sahara Desert as a result of cross-bedding. Okay. So there are a number of different types of sand dunes. Here they all are: Barken, transverse, longitudinal, parabolic, and star dunes. I'll show you the next slide. I have a picture of them. But the wind direction, the landscape, and the velocity of the wind really puts the sand in a number of different patterns depending on those variables. Okay, so you can have Barken sand dunes, which have like a crescent type shape with the tips pointing downwind. So the wind direction is here. It's that crescent shape. Okay. Then there are the transverse dunes. Here you have the troughs oriented at right angles from the prevailing winds. So here you'd have the common transverse type dunes. Brackenoid dunes are kind of like an intermediate between Barken and transverse dunes. Okay, so you can start to see that maybe they're forming that kind of crescent shape. So it's like a mix between these two. The longitudinal dunes are long ridges of sand that are parallel to the prevailing wind. Okay, and the sand supplies here are moderate. Parabolic forms these kind of parabolic ridges of sand here, almost like as if someone's like bulldozing in this direction, and that's really the wind is just pushing them into these kind of parabolic shapes here. And then the star pattern is what it means by star is that these ridges are kind of form a star shape, and that comes from winds that are variable in direction, and that's what we see in these desert type landscapes. And that's what you see in deserts. Deserts, the sediment that moves around by the wind is abraded as it kind of runs into other sand. And so a lot of the sediment that you see there can be kind of polished sharply in certain directions as a result of endless prevailing winds blowing on it. And it can create a bunch of different types of depositional features